Welcome. Let's take a look in this video. I wanted to show you a quick thing. Let me just lay down a GeoNode here, drop inside. Basically, I think it's quite important to know how to scatter different geometry to different points. And there are, of course, countless ways of doing this. I watched IndiePixel's latest video where he did a similar thing in Vex, and it's of course really powerful. And I also remember there was a video from Entagma a while back. I think it was the Kit Bash veins setup, and there they have the same situation where they were copying different primitives to points, and they did it, I remember back then, in a really non-procedural way. And I even thought about this could definitely be improved back then, and I wanted to show you this quick technique that I came up with. It's quite simple. Let's just lay down this grid. Let's just scatter some points there. I don't want it to be too big. Let's just get closer here, drop the points. So we have 25 points in there, and the way that I like doing this is basically laying down for each point that we'll use soon, and I want to create an attribute for each of these points. I'm laying down an attribute wrangle. Let me just call this set IDD. So, or let's just call index, set index. All right, and we want to be able to generate a number for each of these points, and later inside the loop we want to access this value, and then depending on the value that this point has, we will copy a primitive to that point based on this value. So we want to create a integer attribute, so it's going to be an int. And actually, let me just think. I think we need it to do as an attribute, not as a variable. So I'm just gonna call this index. Okay, and this index is going to be a random number that we're gonna fit to a near range. So let's just type these two functions, wrapping one inside the other. So it's a fit, wrapping a random function, and the random function in there, let's just type the ptnum as our seed. Also, we could include a channel to have a better control. Let's just call this seed. All right, so after jumping out of the random function there, we are in the fit function, where we are going to fit this to a new range. So this is basically going to be a value between 0 and a new channel that I'm gonna call max. All right, so this should be it. Also, this gives us a little warning here in green that we are casting a integer attribute to a float, because basically this is returning a float value. So we can just implicitly cast this as an integer, and this warning goes away, which I usually like to do. I don't like that little warning. So let's just click here on this little button on the right. This is gonna create us our spare inputs for us. And let's just give us some space. That's good. And all right, so our seed, it's there, and our max value is there. Let's just not carry about that for now. Let's just set up our for each first. And what we're going to do is lay down a copy to points, because we're basically going to copy primitives to these points, and just connect these like that. And let's lay down a switch node. So this is basically what's going to control which primitive is going to be copied to the points. And how are we going to set this up? Let's just create some platonic solids. Let's keep it like as a theta tetrahedron, sorry, platonic again, maybe a cube, and a new one, maybe a icosahedron. All right, so we have 3 primitives there. Copy to this. Maybe they're just too big. Let's just do like that. And the switch doesn't have a logic yet, so it doesn't know which of these primitives to pull. So we have to reference, make sure that the switch have access to this attribute that we just created. So basically, every time the loop runs, one point will be evaluated. In this case, this one right here, and you can see it has a index of 0. So we will tell the switch to check which attribute this point has, and then basically it's gonna pull the primitive that it's connected to the first input, so the first connected prim. And how we're going to do this is just reference this in the switch node. Let's just create a spare input. This is going to create a little channel for us. I'm going to drag the for each begin there, and we are going to reference this as a point. Use the point function, where we are referencing that point on the for each begin, and we are accessing the index attribute from the point number 0. All right, and so let's just do it differently. Just copy the first there, and let me just try to figure this out. The point, maybe I'm missing in it oh yeah, of course. I'm sorry, I'm missing a argument here. So we have the path, and then we have the attribute, but before that we need another argument to tell that we are referencing the point number 0. Yeah, this should do it. Let's just clean this up and connect it back. All right, sorry about the hiccup, but we are back on track. And basically this is what the switch is doing. It's checking for the point attribute that we have there, the index attribute, and then it's gonna call either one of these incoming primitives. And there is another thing that we could implement, and that I quite like doing, and it's quite important, because if you think about this, if we had another one here, the fourth, let's imagine there is a fourth, and it's a teapot. So basically, if we connect this to here, the switch is hard-coded here. Actually, our index is hard-coded as a max. We input that we were only 3. So every time we put something new here, we have to change this, unless we could we create a function in here and see, all right, how many points or how many primitives are connected to our switch, and then set that as our max value. So there is a function that does that, which is quite handy. So we are going to see here, I think it's OPN inputs, so operator number of inputs, and we just need to reference the switch. And I can do that either like this, just typing the path to the switch 1, and this is gonna return us 4, which is perfect, and it's working. You can see the teapot is there. We could also just create a spare input and then reference this as -1. Doesn't matter. The main thing is that this little setup here allows us to have countless numbers of primitives here and thousands of points, any number that you need or want, and copy always a different prim to the points. So let's just leave this as a octahedron because the teapot has unnecessarily a big amount of brims. And right now we could keep just to prove that this is working. If we put a torus here and just let's reduce the size of it to 0.1 as well, and I'm gonna put there, and then you see they get all shuffled and reassigned. And you remember our little seed channel that we created also is still working, and then we can copy, they get basically reshuffled since the seed is changing. It's super handy thing, super simple to set up. And before we finish this up, I wanted to show you another quick setup that I'm working on, and where this is basically being used for scattering the modules. And this technique, I used something pretty similar back in days when I was doing the procedural buildings. And if you haven't seen that, you could check out my Twitter feed on previous posts. But anyway, let's let me just open up the other file and we'll be right back. So here we are. This is basically a very simple shape generator setup that I came up with using L systems in Houdini. If you're not familiar with it, it can be really daunting at first. It has its own language, to be more precise. It's a edge rewriting system. It's pretty old. There are tons of papers about this. There are books about this. It's something that it's in Houdini. Most people maybe check it out a couple times. Maybe they do something with it. Maybe they just let it be. But there are some applications where you could definitely make use of it. In this case, just for shape generation, it's quite cool. There are some pretty interesting videos from King Gosens that I think Anastasia Opara recommended in one of her talks, and it's definitely on my resources page and at Particular, and you guys could check it out. He goes a bit more in depth about this. It's pretty interesting, creating like random shapes and using them to like mirror and then extrude the shapes. It's pretty cool. The link will be in the description as well. So, but basically here it's extremely simple, broken down to the rules that we have. So at each iteration, let me just go back here and put it at iteration 1. So let's imagine this is based on iterations, and then we have rules. Each time the loop runs, it's gonna check for the rules that you have in here. And this is like one of the most simple things that you can do, but works pretty well in this case. So it basically, at every time it runs, it's gonna check. So F means one step forward, and plus means turn right. Since this is a turtle stepping system, I think that's could be the name that it's called. I'm not sure right now, but anyway, you imagine there is a turtle in the origin. It's gonna take one step forward, which is basically what this F means, and the plus means that it's stored that the next movement that it does, it's gonna go to the right, and then if it's a minus, it's gonna turn to the left. Let me just show you guys the help for this. It's quite, I would say, well documented in Houdini. There's not many crazy things there, but there's definitely the base for you to understand how it works. So there are also pretty cool examples. So yeah, edge rewriting. There is a little introduction, pretty interesting stuff. Back in the days, I was pretty interested in L systems, and I read a lot about it. But basically, it's a system that can create tree-like shapes, and it's quite cool. But anyway, I won't go too much detail about that in this video. Maybe a future one. The main thing that you have to understand in here is that this will basically create, at each iteration, it's gonna either turn left or right. So this is how it works for now. So you can see here at every iteration, it makes a decision to turn somewhere. And then if it goes to float value, that happens, but let's keep it on integer. So this was also used when I was considering about making a dungeon generator, and this setup was pretty much the same principle. But just give me a sec. Right, so in this case we just have like this curves being created, and I just transform it back, put it on the grid. Since we have overlapping points there, I just fuse them, and I create a unit grid which is 1 by 1, and this is gonna be copied to the points, and this will always obey the grid. And if you change the seed, by the way, I mapped the seed of the L system to the F, $F, so I can just scroll and then check out some interesting shapes. And so this basically is gonna happen with all the curves that we create. And at this side here, I basically turn this all into lines. I get rid of the primitive. And if you take a look here at the primitive numbers, we have one primitive per edge, so to speak. And at the resample, there is something happening that's quite important for the setup to work. I'm also creating the curve view attribute, which basically gives me a attribute at each point. So I can tell that number 1, for example, just by this value, that it's a point that is sitting on the middle of an edge. So these points will then basically be used to copy things to it. In this case, we will be working with something like a wall or a window system or a door system. So I know which points to look for later. And at this side here, we are actually just getting rid of everything inside, and using this little wrangle here, I basically reconnect all the dots. So if I show you this, let me just flag this. Actually, let me flag this one. You have the skeleton, so to speak. All of the points inside are connected, and then using a poly wire on those curves, I can select in this second section all of these points that are inside, and I just promote them to the primitives that they belong to, and this can get rid for us of all those things inside, and then we just stay with the curve. And so here I do like the triage, where I split all of the important things that I need for the later parts of the setup, which I haven't built yet. This is just the first R&D part where I was just thinking about this and trying some stuff out. And so basically, you remember the curve view attribute that we get. So I just transfer it back to these points here by proximity, and then I delete all of the points that are not the middle points. And then also at the same time, I go back here to the copied grids that we had in the beginning, and I do a polyframe. So let me just show the normals. So this I'm using the primitive center in this case, which is not very used many times. Oh, actually not, I'm sorry, I'm just using the tangent as n as tied to edges. And then if I resample this again, I'm gonna get a point in there that has the normals pointing inwards, which is quite important for us. As it doesn't matter if it's inwards or outwards, as long as all of them have the same, they obey the same logic. So after that, I end up with these middle points that have all the normals pointing inwards. So this is quite interesting, and we can use this, for example, to copy them the modules to this. So just to show before we continue, here I'm just setting a floor curve, so basically the outer curve that we can then do all sorts of things with it, and then at the same time we can just also create a polypath and create a primitive out of this. So this could be used for a like a floor geometry, or for another subsystem that will create the flooring, so multiple floors, and this could be used for that. And just since we have access to the geometry, it doesn't do any harm just to have the center of the cells that we could use for something later. I haven't figured out yet why or for what, but it's nice to have the information there at your disposal, so you could revisit it and then use for something in the future. I was also studying some things about how to keep the internal edges and maybe have some interesting shapes, like maybe rooms with different shapes, but still looking and thinking about how to do it a good way of doing that. I've done this in the past, but different techniques, so I'm always trying to find new ways of doing things. And so now back to the setup that we were talking about in the beginning of the video. This is basically the same logic that we had there, and then I just prepared here really simple thing so we could just test out. This is basically the same thing. Actually, I didn't add a seed here. Let me just add a channel seed, so we can swap and change some of the values of the modules, and it should be created. Yeah, it did. So this is what you can get with this really simple setup. So in here we have either a box, which is a wall, and since we have the normals in our modules, in our points, all of the things that you copy there, they all face the same direction, which is basically the most important part of this. Otherwise they would all face a global orientation, and this would not be possible. So but basically this is actually just the most simple thing you can do. For example, we have here a window, I think, and if I change this, so you can see all of our windows change in size. But there is something that we can do here to make this even more interesting. So let me just show you guys, take this window as an example. Let me just pull this in there. So let's think about this for a minute. We have this system here that is creating, like in this case, doors, walls, windows, everything. But it's nice if you're doing something like this to split this, and then maybe have one subsystem that handles all the doors and all the windows and walls, because then you can be more specific and then create things to that type of module that basically fits better to that context. But in this case, I wanted to show you that it's quite easy and cool to be able to vary this at each copy, because since this is a loop, we have of course the iteration that the loop is running, and we can access this reference to this node, the metadata node. So let's just, in this box which is basically creating the width and the height of the window, let's just create a spare input. So I'm just making this really simple just to prove the concept that I'm trying to convey. And if we drag our metadata node in there, but actually let me just do this different this time. I'm just gonna hard reference it, because you can see that it is possible to do it. Let me get rid of the spare input. let's accept. And then, so the size that I want to vary for now is this one. So we want to go from a range of maybe, let's say 0.7 and something ridiculous like 0.1 or something. So let's just make a fit 0.1. You see that this type of combination of fit and rand I use all the time. So we want to reference that meta node. Let me just rename this for something simpler, metadata. Whenever I'm referencing this one, it's much easier to rename it. So let's just reference it as like this, metadata. And we want the iteration attribute. It has to be the 0 since it's a one-dimensional. And let's just vary this from 0.1 to 0.7. So you're gonna see it should compile. Let's just double check if I didn't get anything wrong. Oh yeah, I'm sorry. Of course, this is completely wrong. I forgot to reference actually this content here should be inside the detail function. So let's just put this inside the detail, and this is actually our random function. So this should compile now. So you can see our windows, they get assigned different widths. And this is just an example you watch of all the things you can do. So basically at every time a module gets copied, you can vary all of its parameters. And you can go really crazy on this. You can create a subnet. So let's say we have this here, and then we create this as a subnet and just call this a window module or something like that. And if you jump inside, you have this, and you can create all sorts of things. Like every time you reference this, you can still reference it like the same way. You see that the path here changed, but you can still reference the same metadata node that we did. And then if you do this, if you use this as an iteration, every time this module is created, it's gonna be a unique thing. And it's so powerful that this is basically the most used thing that I was doing when I created the procedural buildings back then. So this was all based on this types of logics. So I hope you guys enjoyed this. I think there are a few things here that are quite interesting and really powerful, and you just have to see how this could fit your projects or your workflow. But I will try to make wrap this scene file somehow in a more didactic way and put it up on the website as well by the time that I post the video. So right now it should be available for you. And well, I would like to thank everyone for the support, and I hope to see you next time.